Welcome everybody. So for the past couple of months, I've been thinking about basically how we can get instances without having to write terribly much code. And after discussing it with a couple of coworkers, including Hans Hoglund, and I came to a kind of realization that it can be simplified and written in terms of a much simpler problem. So here's so I've been working on an extension to GSE called deriving via with Ryan Scott, and Angelo has been very helpful in providing feedback on that. So this is just gonna it's a way of basically capturing patterns like that. So these kind of patterns are very common in Haskell, and usually the way that these are taught is they're kind of lore. They're kind of something that's passed down by people, and people. You can say you can always lift a monoid with an applicative, but it's not really given a name, and it doesn't really have documentation. It's not a hackage. It's not something you can use directly in your code. You would have to basically copy and paste everything with this. And as you can see, there's this works for anything that is an applicative. So it's the same code for all of these instances. But we still have to write them all by hand. We still have to duplicate the code here, which is not very Haskell-y to have to duplicate code like that. So really, this instance works for any f that is applicative. We can lift any monoid through any applicative. And currently, we don't really capture that in Haskell. So really, this is kind of routine programming, as Connor calls it, where we have patterns that we can talk about, but we don't really capture them currently. So, oops, some problem there. So we wouldn't want this instance in the first place because it overlaps with everything else. And there are, in fact, other ways of writing this. For any alternative, we also have f of a as a monoid. So we would like a better way of talking about this. Now, I mean, you could object that this is not a lot of code. It's 2 lines of code, but once we have num, we can do the same thing because we can lift any function, any binary function with applicative, and also to fractional, and also to floating. And this is something that we would really not like to just copy and paste. This is something we would like a more principled approach to. One way of capturing it is with a preprocessor, and that's exactly what Conal does. He has a library that actually allows you to derive applicative for any for numbers, and he captures that with CPP, but we would like to do better. So usually as Haskellers, when we want to attach different behaviors to the same representation, we usually use new types, where we give the instances to those things, and that's exactly what we do. We create a new type called app, and because it is a new type, it has the same representation in memory as f of a. So if you have app f of a, in memory, there's no distinction between that and just having f of a. So that means we can capture this pattern exactly for this app new type. And in fact, if the app data type is an applicative, we can write it exactly as we did before, and we can derive the applicative instance. So there's something wrong with the clicker, but in this way, we're thinking of data types not as just the actual representation in memory. We care about the representation in memory, but what I'm more interested in is the actual properties of these structures. And the properties is what I want to steal from other things. So this is what this would look like with this extension. You would be able to say deriving semigroup, because that recently came up, semigroup in monoid. We can derive it through app of foo of a. And because app is a new type, app foo of a has the exact same representation as foo of a. So if we define an applicative instance for app or for foo, we can derive semigroup and monoid and num and floating and fractional with literally no code. And the thing that this translates into is actually quotients. So the pattern is very simple. The extension does nothing else, but for every method in the type class that we're deriving, we say that it equals a quotient of the same method, but instantiated at a different type, but a type with the same representation as the type that we're defining the instance for. So this way we can get all these instances for free because we already defined the monoid instance for for the app new type. So the way this works is using coercible. And coercible basically lets you take two types that have the same representation, and this is thought through the new types. So every time you create a new type of something, you can coerce it from that new type to the underlying representation. And the way we do this is basically we say mempty is equal to a coercion of mempty for app of f of a. So we can coerce from app of f of a to f of a directly, and we can also coerce from a function of app of a to a function of f of a. So this is all quite a simple mechanism, but it's quite effective actually. And there are a lot of use cases, more than I can cover in this talk. So, for example, arbitrary. There are a lot of ways of defining arbitrary that make a lot of sense. For example, with generics, we can define arbitrary if person has an arbitrary instance. We can define arbitrary if it is an integral, or if it is a bounded integral, or if it is a fractional number. We can define an arbitrary for any fractional number directly. So what I would do for this library is I would create a new type for each of those ways of deriving arbitrary, attach the behavior to the new type, and then say, I want to coerce or derive via this new type, getting all the behavior of that for your new data type. So instead of having a single default method, we have as many as we want, and we can add them outside of the library itself. So we don't have to talk to the library author. We can add them as much as we want. So for regular arbitrary, if we derive it via int, we get the default behavior, but we can also nest these things. So there's a modifier in QuickCheck that generates non-empty lists. So as you see, there are empty lists here, but if we wrap the representation that we use to get our functionality, we actually don't get any empty lists in the output, and we can nest it further and say, okay, we only want non-empty lists of positive numbers, or we only want non-empty lists of large numbers. For example, none of those are larger than 100, but if we add another large new type, we actually get larger numbers. So we can say how we want to derive our which properties we want just through these nesting of new types. So this gets rid of a lot of boilerplate and new type methods, and it generalizes generalized new type deriving actually. But the most important thing that I think is that it captures patterns and optimizations. For example, representable, there are some asymptotic improvements that we can make if we know that a functor is representable in the applicative instance. And we can capture that with that as well, so the users don't have to know anything about that. We can also derive serialization with options. So especially once we have dependent Haskell, we can just lift all the option data types as phantom parameters to the new type, use that in whatever instance deriving we're using, and we can pass whatever parameters we want to give to our JSON deriving or Haskell serialization. The cool part, though, is when we have isomorphisms, which I'm not going to talk about because it's maybe a bit too complicated, but if I have time, we can basically, if two data types are isomorphic, we can get all the instances from the other one just by jumping through some intermediate representation or by going directly through the isomorphic structure. Also, if there are many ways of defining the same type class, like this is a different interface to the applicative class, we can say for every monolith class, we get an applicative structure. So we can derive applicative, but pick the preferred way of defining it, basically. So this is the end. I think I have time for some more complicated examples, but I really want to create a vocabulary of deriving so we can stop talking about deriving as a single concept and start talking about which things can be derived from which other things, and then we can bounce back and forth as much as we want. Just as kind of a crazy example, if two things are generic and the representation is coercible to each other, we can actually derive all of these things as long as the other thing has those instances. Something like this. So there's no code here because GHC provides the isomorphism through generics. So we get all of these things for free for our paired data type without writing any code. And we go through many different representations. Yeah, questions?
This is very cool. Can we use it?
Well, I mean, you can use it by just adding the coordinates explicitly. Basically, you write the method for, but yeah, it works on the branch of GC, and it's in. Hopefully, it might be added to next GC, but I haven't started that proposal.
Very nice.
Thank you. And this is Edward's library, and he wrote a lot of instances for functors, and this can all be derived. So there's a ton of uses for this, but I can't really go through all of that. Anything else?
I think we have to leave it at that. Thank you very much.
Thank you.